Hello and welcome to the Bare Metal programming series where we're building firmware for a Cortex-M STM32 microcontroller. This is episode 11 and today I'm super excited because this is, if all goes well, going to be kind of the culmination of the first phase of this project. Like really a point where, if you took nothing else away, you could end it here. So what we're planning to do today is to fill in the other side of kind of the firmware update mechanism that we wrote in the last episode in the bootloader. And we're actually going to write the firmware updater program today that's written in TypeScript. Now, I could have just written this off camera because we kind of, the project is really about firmware, but I think it's kind of important to nail down the fact that this is a communication between two different things, and that really there is some interesting debugging that happens kind of at that interface as you're exchanging those messages back and forward. And so I think it's important to do that kind of together. So what I'm really hoping is by the end of this episode, we are able to update the firmware using the UART that we've built, the protocol on top, and the firmware updater. That will kind of be fantastic if we can get to that point. So let's not waste any time. Let's just get straight into it and take a look at today's plan. So today's plan, episode 11, firmware update program. The goal is implement the firmware updater code. That's it. We're kind of keeping it simple because this is going to be a lot like the previous episode in a way, where we basically were kind of on a whirlwind, just implementing a lot of kind of relatively complex code, kind of in terms of how much we're tackling at a time. And today it's going to be kind of similar, but as we go, my plan is to kind of write each little part of the firmware updater program and test it against the actual bootloader so that we can kind of see things that are happening and fix the issues that come up along the way. I wrote down a couple of main points here, but they're not like, this is not really a big outline. This is just a couple of things that will take place while we do this. So we're going to be reading the firmware from disk somehow. We're going to be implementing the same flow that's in the bootloader. There's a bunch of constants that are in comms.h and bootloader.c that are just going to be shared between these two programs. And so we can copy pretty much all of those just directly into the program here. We have this idea of a knack, which is what we send whenever there is something unexpected happens in the protocol. Like if there's a timeout, if we get a packet that we weren't expecting, if we get the wrong device ID, all of those kind of things, we send a knack packet in those moments. And that's basically saying that the bootloader is abandoning ship and saying, I'm not taking this firmware update. So we're going to automatically recognize that and just also exit the program with a useful message at that point. And I also want to put some kind of nice logging in there so we get some real clear idea of what's going on, what is kind of an action we're trying to take, what was successful, what's an error. So I want to kind of build some of that in, and that's kind of just in amongst all of the things that we're going to be doing, building, not exactly the same program, because in TypeScript, we've got a different kind of programming paradigm fundamentally, right? In the bootloader, we have to model the fact that this is a sort of ongoing asynchronous process as a big loop with a state machine. We don't really need to do that in TypeScript. Like we don't really need an explicit state machine because we have things like async functions, and so we can just write essentially a synchronous program. At least looks like a synchronous program that actually models this ongoing asynchronous communication. So we're going to get into that. That's going to be pretty fun. Okay. Let's just go straight into it. And I will say that there are a couple of bugs which I've already picked up on, which I know there are at least two of that we can fix just off the bat, and that's in the bootloader code. So let's just go and fix those before they inevitably become a problem in this episode. So the first one was that I know that in the CRC code, actually, so this is in comms.c, I know that here we wrote this function, comms create single byte packet, and we wrote it by kind of copying what was in comms setup, and then we changed it to everything to use this packet. But actually I kind of messed up and I kept this RETX packet here, so this would this would never ever work. I'm really glad I spotted this one, because that would have been annoying to track down. So comms compute CRC for the packet. This should be good now. If we try to compute a CRC for a packet that we send on the other side, it should compute correctly. Okay, the other bug that I noticed was just that when we're actually doing the firmware receive, you will remember that if in this in the bootloader state machine, or at least in this part where I explained kind of the sequence of operations, that at every moment the bootloader would send a ready for data packet, and then in response the firmware updater would send a data packet, and we'll do that in a loop until we've finished the whole firmware, and at that point the bootloader will send a firmware update successful. I actually forgot to put these whole data ready packets in, so it's probably good to actually do that. So the first data ready packet is actually sent at this point, right, when we have erased the application and we're ready for those first bytes. So let's just actually put sending that packet in here. So that's basically going to be copy pasting these lines and adjusting them. So we'll go to this state, and before we go to that state, we will write a packet. So we're going to create a BL packet ready for data, send that packet, and probably we should reset the timer after we do that, because sending a packet is a blocking operation, so it actually takes some time there, and we don't want to waste that time. Let's reset the timer here. So we also need to send one of these packets every time we're ready for new data. So if you imagine here, we're waiting for a packet of data, we write it into Flash, and if we're done, we actually send this update successful. But if we're not done, we should send that we're ready for some more data. Okay, so these are just two issues that I already knew were in the bootloader, but I'm sure that we will find more as we go along. So let's get into it. I don't think we'll need the diagram, but you never know. So the firmware updater program. Here we are, and as we left this program, we've got all of this stuff in here. So we've got a bunch of constants, we've got the CRC, we've got the packet class, all of this stuff that I wrote and we used in order to test that the packet state machine was working. That's all still there. We still got this UART section here, and at the end, this main function, that's going to be where we actually do the whole kind of waiting for packets, sending them, doing all of that kind of stuff. So the first things first, let's copy the new constants into this file. So let's go into comms.h, copy all of these ones that we have, and we'll just dump them into here. And let's just... Alright. I'll leave them in the brackets, there's no reason to really take those out. And then in bootloader.c, we're going to need a bunch of this stuff. So we're going to need like the default timeout, the sync sequence, the device ID, all of this kind of stuff we're going to need. Okay. And let's just replace these with const. Okay, and with the sync sequence, it will actually just be easier to put this just into one big node buffer. So let's do that quickly as well. So just put this here. So we can, because when we have this sync sequence, we're just always going to send these 4 bytes together, right? We don't need to send them individually, so we can just stuff them in a buffer and send that out of the UART. Okay, next, I guess the first thing we want to do is to implement the sync sequence. I think that's probably the most useful thing to do to make sure that really nothing major is happening here. Oh, you know what? Before we actually do this, I actually want to show you how the board looks, because I didn't do this in the last episode. I want to show you how the board looks when we do the firmware, when we run through the bootloader and jump to the firmware, because that's something we actually do. So let's take a look at that quickly. So I switch to the big camera view here, pull out the UART wires, which I really need to remember to put back in. And what you can see here is that right now we're in the main application. So that LED is just flashing there using PWM, changing brightness levels. That's something we wrote way back a few episodes ago when we covered timers. So this button here is the reset button. And if we do this, we're going to jump all the way back to the bootloader and run through the bootloader. So when I do that, you'll see there's no light for about 5 seconds. And then roughly after 5 seconds, that LED is going to start flashing again. And the reason that it works like that is because, of course, we have a timeout in the bootloader. So if we don't receive any packets or if we don't get our sync sequence, if we don't observe the sync sequence within 5 seconds, then we are assuming that the bootloading is not going to happen. So we're just going to continue at that point. So that's why we end up in the main application. So that's good to see, like at least the timeout part is working. Let me wire this back up quickly. Otherwise, when we start looking at packets, I'm going to be really confused. Okay, so that is wired back up. And let's write a function to observe the sync sequence and send the sync sequence observed. Just something to send the sync sequence and get that packet in response. All right, so call this function sync with bootloader, and it's going to be an async function. And we're going to, what does the logic look like in this basically? Well, we're going to have a while loop, which effectively goes on forever. And we will UART.write those sync sequence bytes, and then we will await a delay of 1 second. So the reason that we actually wait for 1 second here is because we're meant to just we're sending out almost like a little pulse of data here, and the bootloader, if it sees that, is going to respond to us immediately, like within milliseconds, within even less than milliseconds actually. And so we'll pick that up. And the reason that we're doing this delay is to basically just make sure that we're not sending them constantly, and then if the bootloader recognizes it and sends one back, we're already sending more bytes. Because if we do that, then we're going to mess up the synchronization that we're trying to create. So that's why there's a 1 second delay between each of these. It could easily be much less. It could easily be 100 milliseconds, and we would still have no problem there. But 1 second seems like totally fine as a go here. It does mean that there are fewer syncs being sent. It means that there are only 5 sync messages being sent maximum. But yeah, okay, that's going to be fine for now. So we will send this this message, and then we're going to be waiting for a packet to come in. And so we could use this function, but we don't want to. We only just want to check if there is a packet, and if there is, we're going to kind of continue. We don't actually want to kind of block until there's a packet. So let's just write kind of a custom thing here. If packets.length is greater than 0, that means that there is a packet and we can retrieve it. So to get that packet, we're basically going to do this operation. And I'm just going to add a function for this. Maybe I don't need to add a function for this, because I guess this is the only 2 places that will have this code. I could also do this, packets.splice from the 0th position. Why is that showing like that now? This is to start, this is to delete count. Delete 1, and then get that. So this is now essentially doing both of those operations at the same time. People really hate the splice function, which I kind of understand. If you look at it, it's really ugly. But basically, it's doing both. It's both retrieving an element and removing it from the array at the same time. And you can do it with multiple elements, which is why we need to say the 0th element at the end here. It's a bit of a tricky one, but in this case I think it will be just the simplest thing to do without, you know, writing a whole function that abstracts it. Okay, so we're going to get this packet, and I guess what we want to do is we want to check if it is the type of sync acknowledged. And if it's not, then I think we can just kind of exit the bootloader. We don't really need to do anything further than that. So if packet.is single byte packet, and that's going to be a BL packet sync observed. So if it's that kind of packet, then great, we're done. Let's just return. And if it's not that kind of packet, then I think we can just sort of exit the program. But before that, I want to actually log like a message that says why this went wrong. So I'm actually going to scroll up here. I know I'm jumping around a bit, but I think just before this packet class, I'm going to add a class called logger. And this is just going to have a couple of static functions inside, which will be like info, which will take a message, string, and it's basically going to do a console log inside and just format it in a specific way. So when we have an info message, we'll just format it like this. When we have a success message, we'll put it like this. And when we have an error message, put it like that. Okay, I'm just doing this really because I want to have kind of these nice logs that have this like sort of symbol out front, because I think it looks cool. All the programs that I enjoyed running as a kid had this sort of look to them, like programs that would do kind of jailbreaks on the devices and things like that. They would always stream out a bunch of things that had these kind of looks to them. It was always super exciting. So I'm going to choose to go with that. And then what we can do here in the sync is to basically have an error log here that says we like wrong, let's say wrong packet observed during sync sequence. And then we can just process.exit, not what I meant. And otherwise we're going to just sort of continue trying to do this. Now we actually want to, we only want to do this until we could time out. So let's add a timeout parameter here. Although in this case, like all of these things are mostly going to be the default timeout. So I will add it like this, but we can assume that it's going to just be this timeout. And let's say time weighted is 0. We'll add to time weighted here. And I guess if we get past this point, we can ask like, is time weighted, is it greater than or equal to the timeout? And if it is, then we can also error and exit, which would be timed out waiting for sync sequence. Sync sequence observed. Yeah, we'll leave it like that. Okay, so I think this works. So we can try this straight away. Let's just remove these things and we will await sync with bootloader, waiting for the default time. Let's just put some logger messages here. Info, attempting to sync with the bootloader. And then afterwards we can just write that we synced. This is going to be a good first kind of indication if this is working or not. Right, so let's open up a terminal. Let's move out of app. TS node firmware updater. And what we're going to do here is we're just going to debug the bootloader. And this will allow us to basically just sort of press play here and run this code and see if we're working. So run this. Hey, that actually worked. So I see here that it's still running something. Okay. So we attempted to sync with the bootloader. We received 18 bytes through UART. We built a packet, stored it, and act, and then we got the message synced. Okay, so let's remove these logs, which are currently inside the little packet builder that we have here on the serial port data received event, because I think they're going to be a little bit in the way. It might be useful just to know if these CRCs are breaking, so I will leave it in. It might be nice also to know how many packets are failing to be retransmitted. What's going on here? Why is this malformed? Leave that one. We definitely don't want to know about all these things. It might be useful to know about retransmits, so I'll kind of leave this stuff in. Okay, alright, we'll come back to that. We might do something with that. Okay, so what's the next thing, right? Because now we sync to the bootloader. In the bootloader, what the bootloader is going to expect that we do is then send a device ID. We're going to send a firmware update request. So we're saying, hey, we're synced with you, we're in a communication line, and this is what we want to do. And the reason that we have to send this is because you can imagine that you might actually want to have various optional things that could happen from the bootloader updater, the firmware updater program. You might want to ask like the bootloader version. You might want to ask the firmware version or any of these kind of like query level things. So these could all be different requests, and it just so happens that this is one request that has a kind of flow, and we're only implementing that one for now. So that's the reason that I kind of put this in as the ask for a bootloader update. Like otherwise, if we had multiple paths, this would kind of be wait for command, and then we would do different things based on what our command was. So the next thing we need to do is send a bootloader update request. And for that, I think it will be useful to actually sort of recreate this this function that we have in the bootloader, which is send a single byte packet, or create a single byte packet. So I'm just going to add create single byte packet here. We're going to have the byte which this is based on, and we will just return new packet, which is of length 1 and is buffer.from byte. CRC is obviously computed automatically from that. So when we actually come to send this, we're just going to await. It's going to be the firmware update packet. So packet.create single byte packet, and this is going to be BL firmware update request. And then we're going to send this packet, so UART underscore write. Now we shouldn't use UART write actually. We're supposed to use something else because we need to have this idea of being able to retransmit our last packet. So we need to use this write packet function. Yeah, I forgot about that. So write packet, firmware update packet, and we need to then call toBuffer on that. Okay, so let's make some log some information here. So this is going to be sending requesting firmware update, and then we need to try to then receive a packet, wait for a packet. But what I want to do actually here is also, well, one, I want to build the idea of the timeout here. So we need a timeout, and So exactly the same code as before. If, or rather, time weighted plus equals 1. If time weighted is greater than or equal to the timeout, then we will well, I'm just thinking for this it might be better not to. I don't think it's going to matter for this program in particular, but it might be nice to not actually throw an error at this, like completely exit the program, but rather just throw an error. Because we might want to use this for like attempting to receive a packet, in which case it would have been useful here as well. But say timed out waiting for packet. And what we can do now is, this is now completely fine, but let's write another function called wait for single byte packet. And that will be a function that also takes a timeout, which will be the default timeout. And that will call wait for packet. We'll call that with our own timeout. And then when the packet comes in, we will check if it's the packet that we're looking for. So if packet, and I guess we need to take that as a thing here. So if packet dot data at 0 is equal to the byte, or rather if it's not equal to the byte, then packet's not equal to 1, or the byte is not equal to the one that we're looking for, then we will throw a new error, unexpected unexpected packet received. Unexpected packet, expected single byte by the toString 16. Yeah, okay. And then we can just catch down here based on any error that we happen to get. And when we're explicitly waiting for a single byte packet, maybe at this point then we could do the exit. I don't know, I'm still feeling this out, so this might not be the actual way we want to do this. In that case, we'll just, whatever the error message was, we'll just pass that along and exit on that. Okay, so now we should be able to use this to kind of get what we're looking for. So we can wait for single byte packet, and the packet we're looking for is firmware update response. So that's basically that the response was our firmware update was accepted. So it's going to be firmware update request accepted. Okay, so what happens after that? Then we're expecting to receive a device ID request. So at this point, we expect that the bootloader is going to ask us a question. So we need to kind of just await the question here. So we're going to be awaiting BL packet device ID request. So that's going to be a success. This is going to be waiting for device ID request. And then when we get that request, what we need to send back is the device ID. So in this case, we've hard-coded it up here. It's going to be 42. And we need to build a packet that isn't a single byte packet actually this time. It's a 2-byte packet. So the packet is going to be, this is going to be the device ID buffer. I guess we could just make a packet from it. So it's going to be a new packet of length 2 and buffer.from. And we're going to have BL packet device ID response and device ID. So 1-byte device ID. Then we do write packet device ID packet.toBuffer. Okay, good. So we won't say that's a success because we'll just say responding with device ID, and then I guess we could put it here as well. Device ID.toString16. And then we are going to be waiting for a firmware length request. So the firmware length request is basically them asking how large is this in bytes, and that means that we actually need to, at this point, read the firmware image. Like, probably we want to read the firmware image at the beginning and have the information ready to go. We need to encode that into a packet. So I'm just going to bring in the standard library functions here for the file system. So bring in everything that is in the fs module under the name fs, and everything that's in the path module under the name path. And we actually want to use the asynchronous promises version of that library. So let's reading the firmware image. So const firmware image equals await fs.read file, and it's going to be I've got a firmware image here in the main directory, firmware.bin, so this is just sort of the current build. And we'll do process.cwd, or actually we need to create a path from this, so path.join process.cwd, and just right now we'll hard code this name, firmware image. We need to call that function. And one thing is that the firmware images now, they're currently, the way they're built is that it's the full image that gets written to the device. So it's bootloader first and then main firmware image. If we were distributing these firmware images, actually we would not distribute it in this way. We would distribute just the main application. But for now, for making life a little bit easier, we can address this later. I'm just gonna throw away the bootloader part of this file. So let's bring in, we're making bootloader size up here. So the bootloader size is 32 kilobytes, and we will, when we've read the firmware image, we will just do bin.slice from that bootloader size. So that will just give us the main application. Okay, and then I'm just going to create a firmware length here. I don't really need to make this, but it's a little easier, I think. And then let's write a success message that we read firmware image, and that it's OX, or we'll just do this one in firmware length bytes. So that was the size of our firmware. Okay, so now we've got something to respond with, right? So let's create a firmware length packet buffer, which is going to be a buffer.allocate 5 bytes. Why 5 bytes? Well, we need 1 byte for the message tag, this part, right, that says it's like what kind of message it is, what kind of packet it is, and then 4 bytes to store a little endian uint32 value, which represents the size. So that's what we need to pack into these 5 bytes. So the first byte, of course, is the BL packet firmware length response. And then what we can do is we can use the nice utility methods that exist within the buffer class, like write uint32. And this is one thing that I really don't understand why they did this, but you have write uint with a small I 16BE, and then you have write uint with a capital I. And I don't think all of these are actually valid, right? They're valid in certain versions, but in any case, we need to write a uint32 little endian. And the value we're going to write is just the firmware length, and the offset that we write that to is offset 1. So that will write into the 4 bytes from 1, 2, 3, 4. Okay, now we can create a firmware length packet, which is a new packet, which is of length 5, and the data is this buffer. And then we can write that packet. So let's write that packet, firmware length packet. .2 buffer. Okay, so responding with firmware length, and at that point, if that's successful, we don't actually get a message. We will receive a knack from that if it's not successful. But if it is successful, that is the moment that the bootloader is going to start erasing its application, its main application. So what we're going to do is we're going to wait a little bit of time to allow the bootloader to erase the main application. We know that it takes a few seconds. Can take up to a few seconds, so we will log that that's what we're doing, waiting for a few seconds. I'm literally going to write it like this: a few seconds for main application to be erased. And you know, this is kind of maybe a stupid thing, but I'm going to do it like this just so it doesn't look like it's stalling. I'm going to wait 3 seconds. I'm just going to write this message 3 times. Okay, so at that point, I'm just realizing now, let's deal with these knacks. So let's deal with the knacks up here, just in this area where we process packet UART bytes into packets. And let's do this. If we get a knack, then just exit the program. Like, we know things are not going to work out. So we can check that by checking if it's a single byte packet, and if that single byte is BL packet knack. So if it is, what we will do is logger.error received knack exiting. So if we get a knack, we exit the program. And we'll see that in our log as well. So basically, if we sent this off, we would probably see this like, hey, we're waiting for the main application to be erased, but then very quickly we would see, oh, we received a knack, so we're exiting. So that should work. Okay, but at this point, after this, we're then expecting to go into this main kind of receiving firmware loop. So we know already that they should be sending us a data ready packet. Well, we actually wrote that part here. So what we need to do actually is to, what's the easiest way of doing this? I think what we're going to do is have a while loop which is just while let's write the condition here, let the number of bytes written be 0, and while the number of bytes we've actually written is less than the firmware length, then we are just going to continue doing stuff. And at the beginning of this process, we will await a single byte packet, and that single byte packet is going to be BL packet ready for data. So whenever we get a ready for data packet, we're going to blast out as many bytes as we can. So how do we do that? This is going to be our firmware bytes. I don't know, what's the best name for this? Yeah. Packet bytes, data bytes. These are all terrible names. Okay, so this is going to be the firmware image. We're going to slice from, basically, we're going to use the number of bytes written as kind of where we are in this process. So it's taking everything from this point to this point plus packet data bytes, which is 16, right? So we're going to try to grab 16 bytes and send them out. Now, the issue here, it's not really an issue, but it's something we need to keep our eyes on, is that when you do slice on a buffer or on an array or anything in JavaScript or TypeScript, if you basically try to slice more data than is actually available inside that array or buffer or whatever, then the operation doesn't fail. The operation just gives you back as many bytes as could be, which is actually quite useful in our case, but we need to just make sure that we don't say we're sending 16 bytes, we need to say we're sending as many bytes as we had available in this point. So only at the very end of the firmware image will this become a problem. But, you know, that's why they call them edge cases, because they happen at the edges. All right, so the data length here is then data bytes.length. Again, not something we really need to break out into a variable, but I will. And then we're going to construct a packet. And the packets that we write at this point, they don't have any kind of packet name, kind of packet marker. They don't have something that says I'm a this kind of packet. We're just sending raw data at this point. So we are filling this packet with all of this data. And that means that we can just do const data packet equals new packet, and the length that we're sending is data length, and the bytes that we're sending are data bytes. But this is a small caveat, and I'm sure you remember from the previous episode that we discussed that in the packet, this is the time when it's useful to get the diagram out. So in the bootloader, in the packet format, I have a whole byte dedicated to the length, where in actuality we only ever need to use 4 bits to represent how much data we have in this buffer, assuming of course that you would never have a 0 length packet, because that just is useless. That makes no sense. There's no use in having that. So if we take that as a given, then we can say that if we were to say that we had length 0, then that would mean that we had 1 byte, and so on up until 15, and 15 would mean that we had 16 bytes. Now, I haven't actually employed that across the whole packet state machine, but we did write it that way in the bootloader for receiving these data packets. So actually this is something I'm going to fix, not right now because I just want to get it up and running, but in the next, whatever the next video is, making a sort of incremental improvement on this, I'm probably going to fix that point in there. The fact that we should use that convention across the entire packet state machine and everything. So whenever we're sending a single byte packet, we shouldn't expect length to be 1, we should expect it to be 0, because 0 plus 1 is 1. Okay, so here we actually need to say that it's data length -1, because in this case, if we were sending 16 bytes, we'd say that we were sending 15, right? Because it's going to ignore those top 4 bits when it looks at this. Okay, so now we have our data packet. We need to send it, so we can write a packet of type data packet to buffer. And what are we going to do here? I think it's worth just logging. I think it's worth like logging excessively at this point just to make sure that things are working. So I'm gonna log that we wrote let's see, wrote data length bytes to wrote data length bytes, and then let's have the number of bytes we've written divided by, or like kind of out of, firmware length. And let's not forget to increment bytes written by the data length. So what happens here is we first wait for the message that says, hey, data is ready, we're ready for some data. Then we kind of figure out our packet, we send it, we increment the number of bytes written, and we log that out. And then eventually we should have written all of the bytes in the firmware image, or we will have timed out waiting for a packet, in which case we'll kind of fail out at that point. But if we made it to this point, there's kind of just one thing left to do, and that is that we need to wait for the final message from the bootloader, which is this the message that says the update was successful. So that's a very last point. Let's await that packet. BL packet update successful. Update successful. Let's log that. So logger dot success firmware update complete. Okay, and then what we should do kind of at the end of this program is finally, when we're done with the whole program, close the UART, because that serial port will stay open and this program will stay running for as long as we have that asynchronous object kind of open and running. So let's close it up. That will actually exit the main program and we'll be done. So we just wrote a whole bunch of code, and now at least we've got an easy way of seeing where we're going to have made mistakes. So let's try this out. I'm going to run the debugger. That should throw us into the bootloader here, and let's get this program ready to run. I'll let this run. I'll let this run. Alright, so waiting for ID request, device ID request. Oh, we responded, we got it. Waiting for firmware length. And then it timed out. Huh, that's kind of interesting. I wonder if this is actually... I wonder if... It's probably worth putting some breakpoints down first. Let's see if they send the firmware length request. Let's see if we get to this point. So run this program, run this one. We're syncing device ID. We actually respond with it, we get it. So we timed out waiting for that. Do we send the firmware length? It's crazy to me that we could see that the device ID is taking the same amount of time both times. Huh. Alright, so what's going on here? I guess we're I guess we're getting to that point then. So what's going on here? Do we get to this point? It's really, really weird to me that we're... The feeling that... How are we not getting to any of these breakpoints? I'm not sure what's going on here. I'm not sure why we're not hitting those breakpoints. We really should be. Oh. There's something kind of strange happening here. I'm not quite sure what's going on. Because we're definitely getting the firmware ID packet. Okay, here it is. We send it. Okay, so as far as us getting the response, it looks like somehow what's going on here? So we're here and it seems that we're not getting a packet, or the packet is not being written properly. So let's check that I'm doing this correctly. Device ID packet. Device ID, write the packet, log responding with this, waiting for firmware length request, wait for that firmware length request, request, response, then here we send our firmware length response. But we never receive it. I wonder if there is not something weird going on with the timing here. I'm just going to try something really stupid. Let's just put a 15 millisecond delay in there. Okay. No, that's crazy. Whoa. Okay. I think this actually worked. I think we just got through the whole thing. Look at that. We wrote all these bytes. Okay, so what happened here? The device ID went through, the firmware ID, we responded, we waited for some time, we started writing all of those bytes, which means we were getting all of those packets. The firmware update was complete. At the end here, we wrote 8 bytes, so that's actually kind of nice to know. That edge case works as well. And the firmware update is complete. So that's that. That actually works. That's so awesome, because that 100% means that this is working. I should show on the camera here that this is actually, pull these UART wires out. You'll see that we're actually running the main application. Now you might think, okay, that's exactly the same flashing we saw earlier, so that's not interesting. But it totally is, because the very first thing we do is erase the entire main application, and then we write it in. So the only way that this could happen is if there was first no main application, and then again we got a main application. Hello, and sorry for the break in continuity here. It is actually a couple of days later. And well, when I was trying to film that last part, at some moment the computer just started melting down. Kind of the fan was going crazy, and I realized that it was super hot in this room, and I'd been filming for over an hour, and that things were, not the ideal conditions for the laptop. So I kind of stopped it there, and I was going to let the computer cool down for a bit. And just while it was cooling down, I tried to repeat this this bootloading process, and it was just, for me, it was just kind of to celebrate the moment again. But when I did it, I saw that actually it was failing in some of the updates, so it wasn't consistent. So basically, sometimes it would get to like 300 bytes being transferred, and then it would break down. And well, that was kind of a little bit a little bit depressing when I saw that. And so I kind of thought, all right, I'm going to go away and think about this for a bit, and I'll come back and I'll see what's going on. And actually, I have to say, I spent a long time looking at why, and I chased a few ghosts around in order to try and find the actual thing that had gone wrong. And I just want to kind of take you on a quick tour of that. I'm not going to go through the whole process, but what I originally had thought is, let me see if I can actually replicate this for you now. So I'm going to just burn the firmware. If it doesn't work out kind of in the first or second go, then I'll also just skip over it for now. But if I run the updater now, while we're here, we're waiting for this ID request. Well, this is actually, okay, we got it. And eventually we wait for the firmware length request. Everything is timing out. So that was kind of an issue. That we looked at that, and I actually inserted here a delay of, I think, 15 milliseconds. And that was enough to get things to kind of run. So let's see if that kind of fixes that first part of the issue here. So I inserted this delay, and as you can see, we get to the part where the main application is being erased. We run through, and this is exactly what I saw the second time around, which is, well, not exactly, but something like somewhere into this writing the bytes, it actually fails. So you see here, we get to the point where we actually wrote 512 bytes, and you can see it actually sort of got stuck here on the 496 bytes just before that. And then eventually we just time out. So this is, this was really confusing me. And my first thought about this was that it must be some issue in actually writing the flash, because I was seeing this kind of like, oh, then it takes a really long time. And I'd observed this behavior where it seemed that we did a 16-byte write, everything was going really fast, and then all of a sudden the write started taking more like 1-2 seconds. So what I did was I kind of made a variable here and just kept track of how long this flash write actually took. And if it ever took more than, say, 100 milliseconds, then I would put a breakpoint down. And what I found was when I ran that and I observed the same conditions again, nothing happened. I was never entering that point. So anytime we wrote the flash, it happens really quickly. So then I started thinking, well, how could we get into this situation? Well, remember that while we're in this situation, the actual timeout condition, that's happening here, right? So that's when we don't have any packets available to us, and therefore we're timing out. So we're waiting for a packet to come in, and it's not arriving, and therefore we can't actually do the write. Well, as far as we're concerned on the firmware side, it seems at least that we're receiving these kind of data ready, because we see these 16 bytes streaming out. So the sequence is firmware says ready for data, and the updater application says, okay, here's the 16 bytes I have for you now, up to 16 bytes. So clearly somewhere along the way it seems that a packet's being dropped, right? Because we're losing one half of this conversation. The firmware's still running, right? It's trying to get to this point. It's in the check. All of the flash write is going fine. And if I see here, if I look inside the updater application, everything was also kind of seemed to be going fine, right? I was able to observe that while we were waiting for the firmware, that I could log out and there were no packets available. And what I eventually did, well, I did a couple of things. First, kind of dead end, which was more just trying to put a band-aid on the symptoms rather than anything else, was that I tried to add another timer in here that was just for 200 milliseconds or something, and then I was adding it after this statement. So if 200 milliseconds had passed and we hadn't kind of received our packet that we were expecting, I was like manually asking for the packet to be retransmitted. And that actually kind of worked. That got to a point where the firmware update would kind of complete, all the firmware would transfer. So we would get to the very end of the transfer, so we transferred all of the firmware, and then it would time out waiting for the programming successful message, like kind of the firmware update successful. So that was then really weird. It was almost like we were always seemingly like a packet behind. So that kind of really suggested there's a packet drop. And this kind of adding another timer in was very much just the kind of, oh, let's put a band-aid on it and try and fix it. Very much like this system delay above, actually. So as I looked a little bit deeper into that, why the next kind of logical thing to do was to put, anytime we got to this timed out, well, not waiting for the sync sequence, but anytime we got to a timeout when we were expecting a single byte packet, I started logging out both the received buffer and the packets. And you can actually see that right here. So what I'm doing here is printing out the received buffer and printing out the packets that we have. And notice here that there is a full packet's worth of data in that received buffer, and it hasn't become a packet. Like, we're timing out here because we haven't had the packet we're expecting, but that packet that we're expecting is sitting here in this buffer. So that's kind of the tricky thing here. So why is that not getting turned into a packet? And if we scroll up here to the on UART data event, then the problem actually becomes fairly obvious. So the data comes in, we kind of add it to whatever data we had in the buffer. The reason we do this is because we may not receive a full packet at a time. We may only receive like 3 bytes or something, and then as the next chunk of data comes in, perhaps the next like 15 bytes that makes a full packet, eventually we might have enough bytes for a packet. So we consume those bytes, we put together a packet, we do all of this stuff, and then we push it in and write the acknowledgement. So at that point we have a packet. But imagine a situation now where you might actually, before this happens, right? So remember, these events, this is triggered by Node under the hood by this C++ extension for the serial port library. So it's not exactly running real time, so to speak. And it's possible that by the time we actually get to the point of running this piece of code, that there's actually more than 1 byte's worth of data in the packet, in this event, right, for us. So we end up stuffing, say, 2 packets worth of data into this buffer. And then we get to the problem where we basically make a packet, but then we exit this function, and there's actually enough data to make another packet, but we're not doing it because we've already exited this function. So that's where the problem really lies in this whole thing. And it's an easy fix, actually. We just need to turn this while into this if into a while, and then we're going to try and make all the packets. Only we do need to change these returns to be continues as well. So that is the fix for that. But I really, it was really tricky to find this because actually it wasn't consistent, right? It wasn't consistent about when it was happening, and it wasn't consistent. Like sometimes the firmware update would just succeed. Sometimes I would only get 32 bytes into the packet and it would already fail. Sometimes I would get almost all the way to the end and it would fail. So it's kind of, it was a really interesting one in that sense to find. And if we now try to run the whole thing again, so I'll reset the firmware here and I'll run this, and we can see we should, if all goes well, get all the way through the firmware update. And in fact, we should be able to remove this system delay as well. So if we run this, we actually update the firmware, run this, and then I'm going to try to run the firmware. run the firmware update program. So I'm going to reset on the board, run the firmware update program. You can see that we sailed through this device ID check. And that's exactly the same problem, right? We just, we had sent more data than we were ready to deal with, so to speak, on the firmware update side. So kind of in the end, didn't need the delay and didn't need any of that stuff. And probably if we had stuck delays between every packet that we transmitted, probably that would actually be enough to kind of make sure that the buffer was spaced out enough, right? Because I think I even mentioned earlier in this video that Node kind of runs on this computer on like, I don't know, 10 millisecond kind of sort of async delay. Maybe there's 10 milliseconds between async type events, which is quite a lot, right? That's quite a large number in terms of how many bytes we can transfer across the UART in that time. So I think it's really, I'm actually really, really happy that this works. I'm really happy with this whole transfer process. It's great to see it come across. So I think, you know, and this is just one more thing, by the way. I ended up really chasing a ghost here because I really thought that that system delay was doing something for a while. Because if you happen to run the firmware updater right now in terms of how it is, if you actually run it and you have all of the logs for like if you have the logs set up inside the application, what you'll see is that as you try to do the sync sequence, eventually we start getting bytes back through the UART. We make packets, but all of those packets are malformed and they end up in the bootloader and we get retransmit requests. And because of that, I was like, whoa, what's going on here, you know? And I was putting the system delay in, and I realized what was happening was I was trying to, in some cases, I was trying to debug the application in that sense while it was actually out of the bootloader and into the main application. And of course there, in the main firmware, we have this this line of code where if data comes in on the UART, we basically just send the same data back, but like we shift it up by one. And one property of the CRC is that that's obviously not going to that's not going to work. It's not going to build a packet with a correct CRC at the end. So that was kind of failing. So that all made sense actually. And if you take all the logs out, you actually just see what you expect to see, which is that we timed out waiting for a sync sequence. Because even if we try to do all of this kind of like, well, no, let's do retransmit requests, let's say we got a bad CRC, we'll do like all of that kind of stuff, that works fine. It's working as expected, but it appeared to me like there were more bugs in there than there actually were. So kind of the end conclusion of this is a really great thing in my opinion. It works correctly. I'm super happy with it. I hope that this has been interesting for you and has kind of peeled back the layers of how this stuff works. Now this isn't the end of this series, not by a long shot. As I've mentioned, I think in every episode of this series, we're going to also be doing signed authenticated firmware updates as well. And that's going to involve quite a lot more logic, especially in the bootloader. But it's going to build on this foundation, right? This foundation is now what we build on. So the essentials of transferring the data, doing all of the packet protocol stuff, just like being able to write that stuff to Flash, all of that is going to remain the same. The only main difference is going to be that somehow that firmware is going to have to come along with a signature, and that signature is only going to like match if it's signed with the correct key. And that key is going to be secret, right? It's going to be stored on the firmware as well, so that when we get a firmware update for our application, we will be able to check it and from there like validate that validate is legitimate, and only then will we jump to that firmware. Now there is another problem, right? I think I should be able to show this. I'm going to run the run the application here, the updater. So I'm going to reset, run the updater, and just kind of while we're writing, I'm going to rip out the UART cable, and then that's going to sit there. It's going to try to do its thing, and eventually we're going to time out. Can plug that back in. But now the problem is that the device is actually still going to try and jump to that firmware, and that firmware is very much not valid anymore, right? We only wrote 864 bytes, and that's not enough. We basically need all of these bytes to even execute, like, for any perceivable amount of time on the chip, right? Because the minute that we try to jump into some code that isn't like within our range that we've written, we're going to end up in an infinite loop somewhere, because we're going to have caused an exception to happen. We're going to have entered into a trap and go into an infinite loop. And we should be able to fix it by, of course, like flashing the bootloader again. So if I reset, I run the bootloader updater, the firmware updater, and now it works correctly. But it would be nice if we didn't even jump to the main application unless we knew that we at least got not an authorized firmware, but one that we knew was fully complete, right? Like a firmware that we know matches what should have been sent. And the straightforward way of doing that is that before we send any firmware, as part of kind of the back and forward conversation that goes on between the bootloader and the firmware update application, one of the additional questions to what's the device ID, what's the firmware length, the next question will be, can you give me a CRC of the complete firmware? And then we'll store that, and then if at any point we try to do a firmware update, we'll check against the CRC and we'll make sure like this is actually complete, and if it's not, then we can do something else. Now of course that doesn't help if you then unpower the chip and power it back on, because then you have an invalid firmware but no one has told you what the CRC should be. So in that case, what we really need to do is to actually embed that signature inside the firmware somehow. And well, we're going to look at how to do that probably in the next episode. We're going to clean up some of the other bits and pieces. Like I would like to fix consistently fix this thing that we have, which we only make use of in the data sending section, which is that the bottom 4 bits of the length are all that we should use. And we should offset that by 1 or -1 depending on whether we're sending or receiving, because I think that makes more sense, and it leaves us some wiggle room to having the idea of to be able to use those top 4 bits for something else. So that's probably the couple of things that we'll tackle in the next video. Thank you for sticking with me, and especially for going through this kind of long-winded explanation at the end where it seemed like we'd already succeeded. If any of this hasn't made sense to you, if you have specific kind of questions about it, please leave a comment below. I'll be happy to try to answer that if I can. You can also join the Discord server where you can have more of a real-time conversation, and of course there are other people who might be able to answer your questions. You can also share any of your own projects there. And well, I think that's kind of it for today. I'm really happy with the result, and thanks for watching. I'll see you next time.